Are you timing?
This should time it on the presenter view. All right. Hello. My name is Henry, and my supervisor is Professor Hamid Valipur. My topic is the reliability of reinforced glue laminated timber beams, which are essentially like timber composite materials with a reinforcement material such as steel or FRP. And so I'll go through today like what reliability analysis is. But first, let's talk about the importance of timber. So the carbon footprint of the building industry accounts for 11% of the total carbon emissions on the planet. And so when we're talking about carbon, we're talking about the embodied carbon, which is its entire life cycle, like the carbon produced throughout this entire life cycle. So from the extraction process, such as like mining or milling, to the manufacturing process, such as cement manufacturing and etc. Up until it's used, and even when it's disposed of after a building is demolished. So out of this 11% figure, 5% of these emissions are due to concrete, 3% is due to steel, and the rest makes up the remaining 3%. So this is a significant portion of the total emissions that we emit as humans. So that's where timber comes in. So the good thing about timber is that it essentially can store carbon. So about half of the dry weight of timber is actually carbon. And so 1 ton of dry timber equates to about 1.8 tons of CO2, which is sucked into the wood and stored there as a carbon sink until the timber is burned or it's released another way. So as you can see from this graph, for example, the net carbon emissions from the material of timber, when we're including the carbon storage potential, is actually a net negative. And for CLT, right, so this is cross-laminated timber. This is like an engineered wood product because of the manufacturing of like the extra processes required to manufacture CLT. The net carbon emissions aren't as much as raw lumber, but still net zero essentially for carbon. But we're going to be talking about Glulam today. So Glulam is an engineered wood product, which essentially just means that there's like multiple pieces of wood stuck together. In the case of Glulam, the planks of wood have the same fiber direction, so they're stacked either on top of each other in what's called flatwise bending, but we're going to be analyzing an edgewise bending case with reinforcement inside to ignore like the effects of rolling shear and things like that. But so softwoods such as radiata pine are relatively weak. These are like relatively weak and like they don't have like many strong. Sorry, let me start again. The strength, ductility, stiffness is relatively low, as well as the section sizes. They don't come in that big of boards because of the diameter of the tree that it's cut from. But when you laminate it together using glue, you can improve the section sizing and increase its like consistency essentially, and overall strength of the section. So as you can see from this bell curve, we can improve solid timber by laminating it into Glulam and then reinforcing it with a reinforcement material such as steel compounds this kind of effect. So in my literature review, Professor Hamid provided me a bunch of resources. I guess like my anchor kind of paper is calibration of AS3600 by Stephen Foster, and there's a bunch of other codes and general recommended readings on like reliability principles and specifically on timber. So let's talk about limit state design. So limit state design is what's used in the Australian and New Zealand standards, and it's what we use in structural engineering. So we have our factored load on the left-hand side, and this factored load is said to have to be less than some calculated capacity, so like the strength of the material and the size of the material. contributes to this. And yeah, specifically for flexure, so we're going to be talking about bending today. That's what the equation looks like. And today I want to be talking about calibrating this number, which is the capacity reduction factor. So this number comes from essentially, it comes from the consistency of the material and how often it fails, right? So with steel, for example, in the design codes, we see numbers close to 0.9, 0.8. Concrete, we see like 0.65, 0.85, these kind of ranges. And for timber, it's even less because the variability of the material itself, which we'll get into, is quite high because it's a biological material. There's a lot of defects which can come up, such as knots in the wood, which can reduce this consistency. But yeah, we have to conduct something called reliability analysis. This is this is especially important for timber due to the variation in the material. So limit state design, so just continue with limit state design. The calibration of this number, the 5 factor, if it's too high, we're essentially under designing the structure and it's unsafe, right? So if we gave timber the 5 factor of 0.9, right, in like all of its cases and stuff, we're essentially overestimating how strong the material is consistently, right? And if this number's too low, we're essentially over-designing the structure, we're wasting materials, and this leads to like unnecessary costs and CO2 emissions. So yeah, basically we want to find the sweet spot for this value. Okay, so we're going to be using a statistical model in order to do this. So this is called limit state function, and it's basically just what I showed earlier, but just worded a little bit differently. So R is the resistance function, and you subtract off the loads, and if this number F is less than 0, it means that for that particular case that you've generated, like the structure is broken. But if it's greater than 0, then the structure remains standing, right? So we actually have to conduct a high number of these tests in order to justify it. So for my steel reinforced timber, I've generated 11 million values, and essentially it comes from 1 million, and then we look at 11 different alpha values, so it's 11 million. Okay, so just back to that limit state function, we're looking at an individual trial X, and to calculate this, what we can do is we use a numerical model to model the resistance. So we use finite element modeling, and we randomly generate the geometry, so like the depth and the breadth of your section. We randomly generate material properties such as like the strength of the timber and the strength of the steel, area of the steel. And we apply like a constant load until it breaks. And that simulates a lab test essentially. But because we're generating millions of data points, it's very expensive to conduct these lab tests. So what we do is we digitally simulate it, and it saves time and money. And we just have to make sure that the input parameters we put for the randomly generated parameters are justified by literature. And for SX, the load, we use an analytical model. So this is where we theoretically calculate it using solid mechanics and static analysis. We keep the geometry and material properties constant, but we actually randomly generate a loading parameter, which I'll show you in a bit, to model the load vector. Okay, so in terms of timber, as I mentioned a little earlier, we can have knots in the timber, which causes the strength and stiffness to vary. We can also have manufacturing errors, right, with the boards of timber, which can make for inconsistent sizing. And the timber in flexural tension will experience a brittle failure as well. So here I've shown the section sizing variations. Here I've shown the variations in strength due to like the knots and stuff. And then here I've shown that the steel can essentially make, so the steel is also added as a reinforcement material, which has its own randomly generated material and area properties. And this creates a more ductile section overall. So for the load vector, I was talking about how how the loads are randomly generated. We split the loads into the dead loads and the live loads. So live loads can be like due to pedestrians, traffic, things like this. And then dead loads can be due to self-weightless structure or like partitions which will be there for a long time. And our dead load we map to a normally distributed curve like this. It's relatively consistent. And our live loads, we model to a Gumbel distribution, which is essentially an extreme value distribution. Every now and then you're going to generate a very high value for the live loading, which can cause like an unexpected failure, essentially.
Like a really fat person.
So these are bias values. So they're in the range of 1. They're in the magnitude of 1. Because we have to make sure that our loads aren't biased to a certain building size. So we're being generic for any given building, like whether it's small or large. So we're just saying if we generate 1, it means that the live load that we predict is 1 times the live load that we predict. If we generate 3, it'd be 3 times larger than we actually predict. Okay, so I have to explain something called M. So M is the observed data point. So here we have the limit state function. This is for the case of an area of a live loading area of 50 meters squared, and alpha is 0. So if we look at M being the middle value, this is the median. If we look at M is equal to 1, we're looking at the worst case scenario. And if we look at M is equal to N, this is the best case scenario. So you can imagine on this like roughly normally distributed curve that it might look something like this when we're pointing out those values. But we basically want this observed data point to inform our decision on phi, or the probability of failure, right? So how do we do that? We have to set M as a critical value at some point, such that extreme outliers are disregarded, but the majority of data points are considered. And so that critical value happens to be for 1 million data points per alpha value in my case. It happens to be 66 because we have this requirement in the standards that's been outlined by Stephen Foster of we need a failure of less than 1 in 15,000. And so we look at the 66th worst value from the bottom, and we consider that as our what will inform our decision for phi, or the capacity reduction factor. Okay, so doing that gives us essentially a bumpy curve. It's a little bit inconsistent. Here I've drawn 2 lines. For the blue line, that's for an area of 50 meters squared. And then for the green line, it's for an area of 250 meters squared. But even these 2 lines aren't really agreeing with each other in terms of its shape. And that's because of something called M. It's just like essentially when we observe a data point, how phi is actually calculated. So if we're looking at the 66th worst value, let's just say that's negative 10 kilonewtons. And if the 65th worst value is negative 11, and the 67th worst value is negative 9, right? These can all have various values for load and resistance, but we're just looking at the difference between these 2 values. But phi is calculated by dividing these values. So even though the worst was here and the best was there, essentially our best number was here for phi, but the worst was actually the middle value here in these example numbers. So what we actually want to do is we want to average the adjacent values for resistance and load, and that gives us essentially a smoother curve. So here I have an m value averaging of 1 on either side. And then if we have 2 on either side, it converges our results even more. So yeah, that's basically my results. And then if we take a trial phi value for glue laminated timber reinforced steel of 0.67, yeah, we get these graphs. And yeah, so essentially these are the trial values. Oh, sorry, this red line is the, sorry, these blue and green lines are the result of using the trial value. And we want to keep the probability of failure below this line and the beta, which is the reliability index, above this line. And we say for beams that the typical values of loading for alpha are between 0.25 and 2. So this value is quite justified. But alternatively, we can use the alternative load combinations. So using a slightly different load combinations than what's found in the standards will also give us a more reasonable result where there's not a random spike in the probability of failure or reliability index. But yeah, that's the end of it. Any questions?
No, that's it?
Yeah.
Oh, wow.
It's supposed to be 15 minutes. It's supposed to be 10 minutes, but like, that was 16 minutes, you know?
Oh, okay.
Yeah.
I think they're gonna cut you off.
Yeah, then surely that's fine. Did any of that, yeah, I don't know. How was that in general? Like because I want this to be interpretable by like anyone in the room, not just like the fucking PhD professors in structural. So do you guys have any questions?
No, I think it's
Okay.
Following along.
Was this anything I did too much of or too little of? Do you reckon? Should I talk about anything more, emphasize anything more or anything less?
I think like maybe you can emphasize like, you know, like the basic stuff.
Mm.
Yeah, because like even if you're like trying to like cater for everyone, like your thesis is about like the complicated stuff, not like the that stuff, you know.
Should I talk about this more? Yeah.
No, I think because like if you talk about this more, like you want to talk more about like the stuff that you do, right?
I think I spent too long on this one.
Yeah. Like
That one makes. I think this is where like the actual method
This
starts.
is where your thesis actually starts.
Yeah. So that's like halfway through. Fuck. Whatever. Anyway.
but it was good. 16 minutes.